Okay, let's look at an example of moment of inertia for a composite area. So here's that shape that we've been looking at. I put some numbers on it now. It's 6 inches wide, 10 inches total height. The top and bottom flanges are each a ½ inch thick, this is often called the web in an I-beam. The web is a ½ inch thick. That means that it's 9 inches from the inside top to the inside bottom because it's 10 minus a half minus a half. Okay. Let's find the moment of inertia, I sub x, where the x-axis is the beam's centroidal axis. So where's that centroidal axis? I don't have it dimensioned, but look, this is a symmetric shape. Remember what we said about symmetry and centroid. If you have symmetry, then the centroid must lie upon that axis of symmetry. If you can take this shape here and fold it down upon itself, it would be right at the mid-height here. So our x-axis is going to be right at the mid-height, 5 inches up from the bottom, 5 inches down from the top. I didn't have to put pencil to paper to calculate that centroid because I recognize symmetry. We're going to solve this two different ways. We're going to do one with just using all positive areas, and then we're going to do it again, taking advantage of void areas. See if we can make it any faster. Option one, we're going to use all positive areas, the actual area of the shape. We're going to break this up into some simple shapes. We're going to use 3 rectangles. There they are. We have area 1 here, which is horizontal across the top. Area 3 here, which is horizontal across the bottom. And then area 2, again, goes from inside of the top to the inside of the bottom. It stops short. It's not this 10 inches. It's 9 inches tall. Okay. Note that area 1 and area 3 are similar in almost every way. They have the same area. They have the same, their centroids are kind of in symmetrical locations, the same distance away from here. So we're going to get to use those values, killing 2 birds with 1 stone, as it were. Area 2 is nice because isn't its centroid sitting right there on the overall axis, the overall centroidal axis that we care about. So we know that that one's going to have a 0 AD squared term. So that's cool. The first step, let's calculate the component areas, moment of inertia, about their own centroidal axis. So these 1 and 3 are each going to be 6. So base times height cubed over 12. So 6 times 1/2 cubed over 12 is going to be 0.0625. And that's going to be for 1 and 3. And then I see 2, which is what, for area 2, it's going to be 0.5 inches wide times 9 inches tall cubed over 12 gives me 30.75. Okay, so that's my first column done. Now let's calculate the areas because that's the second one, the second column here. So area 1 and 3 are each 6 times 0.5 or 3 square inches. And the second one is 0.5 inches times 9 inches tall or 4.5 square inches. Okay, so that's all pretty easy. Let's calculate those D distances. Again, this is not hard. It's just that people won't get it right if they skip the step of actually drawing it and labeling. So let's label those centroids. So I'm going to draw them in here. So I have the centroid of area 1 right there in its middle, centroid of area 2 right there, centroid of area 3 there, because the centroid of a rectangle is right in the middle. So that's great. Now I need to dimension to them. And that's going to be, since I know this is 1/2 inch thick, it's going to be, 1/4 inch up to the top. So I'm just doing, if it's 5 inches from the centroid up to the very top, minus 1/4, that gives me 4.75. Remember, I told you these D distances are very simple to calculate. They just usually aren't staring you in the face unless you draw it. So please, please, please draw it. The bottom one down here, D3, is going to be the same value. And D2, the distance between the centroid C2 and the overall centroidal axis, is 0. So now my next thing is to just do some calculation. I'm going to square my D's and multiply them against my areas. So my A1 D1 squared is equal to A3 D3 squared, which is 3 square inches times the square of 4.75. That gives me 67.6875. I usually don't keep this many significant figures, but since I'm showing you in this example, and we're going to be kind of comparing between options, I wanted to make sure I didn't have any round off, so I'm carrying it to this number. The AD squared for area 2 is 0, obviously. So then I get these values here, which is just, again, A times D squared. Now I'm going to just add 0.0625 to 67.6875. And I'm also going to just carry the 30.375 because that's 0 over there. And I get that last column. And then I just add these three numbers together to get my answer, which is 166 inches to the fourth. That would be the moment of inertia of this overall shape about this x-axis, the centroidal x-axis. Let's look at it under option 2, using void areas. Okay. Now this component area 2 and component area 3 are my void areas, and then my large rectangular area I'll show you in a second. It's going to be this 6 by 10. So that's my large rectangular area here. You can see I've overshot my area. What's cool about this large rectangular area is its centroid lies on the x-axis. Now I just need to adjust it with two 2 3/4 inch wide by 9 inch tall rectangular voids. So I get it like that. Note that void 1 and void 2 are basically the same. They are the same. And also note that their centroids lie right on the x-axis as well, the centroidal x-axis. So what that really means is, in this particular instance, this table, this is like the one time you might not need to do the table, and that's because only this first column is really going to matter, because there are no D's, they're all 0. Now, you do have to pay attention when you do, like for the large rectangle, that's a positive 6 wide times 10 inches cubed over 12 gives me 500 inches to the fourth. That's way overshot. Remember, our answer was, between 1 and 200. This is way, way too high. Obviously, I've overshot it because I accounted for a lot of area that actually isn't in the shape. So when I go and add my voids in, I'm actually putting them in as negative numbers. So my void areas are going to be minus BH cubed over 12, or minus 2.75 times 9 inches cubed over 12, and that gives me minus 167.0625 for each one. So again, I don't need the rest of my table really, because all my D's are 0, which makes all of my 80 squared terms 0. So my summation is the same as this column over here. I just do 500 minus 167.0625 times 2, and I get 166 inches to the fourth, which was the same answer that we had with the other option.